Well, this is pretty next level, this question, I think. I'm going to go for it how I did it. I don't think it's ideal, but it did get me the right answer. And yeah, but I'll talk about like slightly better approaches. So we're told that g of x is equal to x f dash x, and f of x is a non-zero polynomial, and then f of x is equal to 0 for exactly m real values of x, and g of x is equal to 0 for exactly n real values of x. And I asked which of these is true. So what I decided to do is just introduce some examples of f of x. Let's make it, no, it can't be a constant, but why not make it a linear function? In fact, I just went with a general linear function. You could do mx plus c. I went with ax plus b. So this is guaranteed to have one root. It's going to go through somewhere for non-zero constants here. Um, so that would mean that m is equal to 1. And now if I do f dash x, that will equal a. So g of x will equal ax, and that will give me another root, n equals 1. So I can see that it's definitely possible that this is true. Well, why not keep going? Let's look at a quadratic. So this could have m equal to 0, 1, or 2, depending on the discriminant. Let's just sort of draw some graphs. So yeah, it could look like this, or it could look like this, or it could look like that. Okay, so if I'm investigating g of x, actually let me just do f dash x first. F dash x is going to equal 2ax plus b. So then g of x is going to equal 2ax squared plus bx. And I'm guaranteed to get a solution of 0. So x, and then it'll be 2ax plus b. And actually, I'm guaranteed to get two solutions here because this will always give me 1 and this will give me 1. So n is equal to 2. And therefore, I found an example. If, for example, if my m was 0 or 1, then m would be less than n here. I found an example of that one. Brilliant. Okay, how can we get m greater than n? Or is it not possible? So let's take a look at a cubic. Ax cubed plus bx squared plus cx plus d. Now this is definitely going to have at least one root because cubics sort of look like this, or they're definitely going to cross the axis. So I'm going to get m equal to 1, 2 if we had a double root, or 3. And then f dash x is going to be 3 ax squared plus 2bx plus c. So g of x is going to be 3ax cubed plus 2bx squared plus cx. I can factorize out the x. Okay, and this is where my method kind of falls apart. I'm sure I could do a little bit more on it, but I just said, well, I'm definitely going to get 0 here as a solution. Now, surely it's going to be, this is a different this is a quadratic, and surely I could maybe get no solutions for this one, but I could get some, like more than one solution for this one. So I just kind of convinced myself without actually proving it that this is definitely possible. It just feels like surely we could get like a repeated root here and then 3 here, or we could get no solutions to this quadratic. Um, b squared minus 4ac, because I'm sort of I'm timing this by 3, like surely that is going to be okay. And so I went with H, and that was the correct answer. It's got to be said though, that is not ideal, is it? I haven't really done that in a convincing way. My first two were convincing. Here it's a little bit hand wavy. It's like I feel like it's gonna be true. Now, having stepped away from the problem and looking back at it again, let's see if we can, show it with certainty. So I want to make sure I've got a cubic with, say, 3 real roots. So I'll have it going up and down and back up. Now, I'd get a root here, here, and here, so m would equal 3. If I now find the derivative and times by x and set that equal to 0, then I don't know what my new function would look like. Well, I could try and draw it, but what I know is that I would get a root here at the stationary point, because remember, I'm looking for x, like forget the x for a moment. I'm looking for the derivative equaling 0. So I'm going to get 1 there and 1 here. And I'm also going to get 1 here. So this particular cubic is going to have n equal to 3 as well. So I've failed to have m greater than n. But I might start thinking about how I could maybe just modify it slightly. And it's all about that 0. Because if I take this same function, but I could move it, like translate it in the x direction, I could put it here, and then suddenly I would still have my m equal to 3, here, here, and here. I'm still going to have a root here where my g of x is 0, my f dash x times x is equal to 0. But then I'm going to get a root here, but I'm not going to get another one because I've made it so it's 0. Without looking at it algebraically, I've just sort of looked at the graph and seen it. So in this case, n would equal 3. Sorry, not 3. N would equal 2. Okay, that is more convincing that 3 is possible, and therefore our answer is H. Could we get 1? That's another thing to think about. Um, yeah, good question. So I'm not sure about that one. So we need it to go through the axis like, well, I'm trying to still stick with m equal to 3. I want it to go through the axis 3 times, but I know I'm always going to get 1 at 0. And yeah, I don't think that is going to, I don't think I can get m equal to 3 and n equal to 1 actually. Um, could I get m equal to 2? Okay, there's other things. I'll leave you to think about it at this point. But what I've done is started with a linear function, got them the same, then done a quadratic and shown actually I could have them the same, or I could have um, n bigger than m. That would be okay. So I got 1 and 2. 3 kind of tripped me up a bit. I just sort of said, yeah, I think it's possible. But my logic was a bit flawed because I kind of concluded that actually maybe I could even have no solutions to the quadratic. And from my graph, I don't know if that's possible. But I then did resort to a graph, start looking at stationary points and this extra one we get from times and by x, compare it, but then modified it and saw that it was possible. All right, I think that's a pretty tough question. Well done.